Hey, this is Steven from LegitTechTutorials and the Green Engineers, and welcome back to my product development series. We are back working on the heat treating kiln. So we're looking at a few different things in this video. We're going to start to design the different parts. So we have the two separate parts. We have the fan and piston mechanism, and then we have the kiln itself, which are the three casts. The outer wall cast, which is just a smooth cast. That one's going to be made out of steel because it's going to stay. And we have the interior form, which is going to have all the ridges on the walls for to put the resistance wire in. And then we have the door former, which is also a permanent former. Permanent cast, going to be made out of steel. Thin steel, and go with thin gauge on the side and thick gauge on the outside, and go all the way around, and then we're going to pour into that. So I think that doing the piston part would be funner to do. So let's go ahead and do that first. So this is something that I don't know if I've ever shown on a video yet. I've used it quite a few times. It's called SwiftCalcs. It's a online tool. It's kind of like kind of reminds me of programming. It's kind of like a cross between programming and Excel. It's basically a thing that you could set up calculations doing with variables, setting variables, and then being able to change the values and have it recalculate those variables. So it's way quicker to set up than an Excel spreadsheet, I think. I don't know if it's as easy to read, but it's pretty quick to set up, and also they have a lot of material properties and stuff that you could do. And the other thing that they have is they have ways that you could drive dimensions inside Fusion 360 with a plugin. So you could actually pull dimensions from Fusion 360, plug it into here, and when you change these values, it'll actually change the dimensions in Fusion 360. So this one's pretty big at doing different things. One of them that they said that it was supposed to be pretty good for was obviously metals and stuff, because they have quite a bit of different materials. So like you insert, there's a materials, we have material general, insert general, materials library. They have a giant material library and mixture library of different things. So here I have methane pulled in. And so what we need to do is we need to do some thermodynamic stuff on how big we need to figure out the diameter of the cylinder to be. And how much power that's going to cause for the fan. Also, we need the stroke, how big the stroke is going to be, so that we could machine a piston for it and machine some rings. So, because this is probably going to be an oilless system, but yet you need a full seal, I was thinking to make making it out of having like some sort of well, I was originally thinking of doing something like the 3D printed what's that called, the 3D printed things for bushings, but generally those are not for high temp applications. So maybe some what's it called? Teflon. So Teflon melting point 326.8 Celsius. So I think that for most applications we should be pretty good, because also that cylinder is going to be cooling down when you push gas through it. So it should keep these rings relatively cool. So the main thing because if it's steel on steel, it's going to start to get hot and it's going to start to wear, which are both things that we don't want. Well, getting hot is actually a good thing, so maybe it'll help keep the inside of it hot. But generally we're probably going to want no wear there, because it's just going to be, you know, better off. And also you'll have more cycles on the fan before you have to pump more gas in and expand it. Okay, so let's go ahead and start doing some variables. So you'll see how this works out here in a second. Go back to this one. So throw. So what you do is you do that, and then you put in like an input slider. Let's just reload. I didn't like that I was doing it on another page. The box. So you go into variables, input slider, and then this is throw. And then you calibrate it with the unit size. Okay, so then let's say that this is in inches, so units, IN, inches. And step size, 0.1 of an inch, and we want a maximum value of up to maybe 6 inches. Minimum value obviously is 0.1. Same thing with this one, minimum value 0.1. 3, step size 0.1, inch. Okay. So we got diameter cylinder throw. So then from there we can calculate the volume is equals to throw times diameter, basically. So 2 pi r. So you have 2 pi r is pi r squared. So you have pi, let's see, I don't know if it has 3, let's just do 3.14 times r, which is diameter of cylinder. Squared. Pi r squared, so throw times pi r squared is volume. And then you type in volume again, and I'll tell you that number. And then you could say change units, say inch to third. So we have 1.6956 inch. So this is definitely going to be at least, and then you'll see right here I'll change the value and it'll change here. Change this value, it'll change there. So 1.5 inch with a 6 inch throw is 10.5975. Okay, so then let's say that we have a here, let me let my cat out really quick. She didn't know why she was coming in here. So one of the variables we also need to come up with is our quote-unquote combustion chamber size. So I'm going to say combustion. I'll just say expansion chamber size. So I forgot to put in the input slider. Combustion chamber size, and then this is going to be inches cubed. And minimum value is going to be 0.1 steps. Maximum value is going to be like 20 or so. One second. sorry about that. I had to do something really quick. So let's get back to it. Okay, so I'm just going to change it. You'll see why in a second. So expansion chamber size. So let's say if that's 10, let's say it's like 4 inches cubed or whatever. Even though right now, let's just disregard that. That will probably be used later on. So we have expansion chamber size. Alright, so another variable I'm going to put is current throw. And max, I wonder if I could put a variable as maximum value. I wonder if I put overall throw. Huh. That would have been nice. I wish that this could be set maximum as overall throw, so that way it's always, the sliders always change. It changes to the overall throw. You should probably put that in Swift Calcs. Anyways, so current throw. Okay, so basically what we're going to look up right now is we're going to look up some Alright, so let's look at some let's look up some thermodynamic equations. So there are mainly, the equation that we're looking for is, if I could remember correctly, heat and matter, pressure is PV, I believe it's PV 1 PV to the 1.4. So here's isothermal, so that means no change in temperature. We have adiabatic, which means no transfer to the adiabatic means basically no transfer in or out. Isochoric, that one. This one's no change in pressure. Isochoric, no change in volume, I believe. Yeah, so change in volume equals 0, change in pressure is 0, change in temperature is 0, and Q is 0. So let me see if there's one for pressure. Here's entropy, change in entropy. But here's change in work. So change in work is going to be very important. So nRT, ln, V2 over V1, N being number of moles. And so these are ideal gases, which is what we would be working with. So work equals PdV, isobaric, where pressure change is equal to 0. Volume, obviously it's not going to be this one. There's no work if no volume changes. Change in temperature equals 0. So that's another one it could be, isothermal. Adiabatic, Q equals 0, CVT2. So this one, I'd probably go with this one, nRT. So R is the constant, I forgot, Rydberg's no, it's not Rydberg's, it's some other name of a constant. So number of moles times the R constant times the current temperature in Kelvin, which is whatever it is in Celsius plus 273, ln, which is natural log, volume 2, your final volume over first volume. So that's the amount of work that would be done. And so we're not really too worried about change in pressure, so that's kind of just like how much work we want the piece to do, we want it to do. So here's the ideal gas law, which is nRT, PV equals nRT, pressure of an ideal gas, pressure equals number of molecules times the mass of one molecule times the, what is this small b? I guess it's volume. No, something else. But there's another one where it's, I might have it in my backpack, but it's not around here. No. Let me see if I can find it. So PV to the 1.4 is equal to PV to the 1.4. I believe that's what it is. So yeah, so there you go. When air expands adiabatically so adiabatic means that without gaining or losing heat. So nothing's transferred through the walls of the cylinder, which we'll just say for this point, for this case it is, which adiabatic Q equals 0, right? So no, without gaining or losing heat from anything, its pressure P and volume are related by the equation PV 1.4 C, where C is constant. Suppose that a certain constant volume blah blah decrease order rate cubic per meter is okay. So that's what I was looking for. So it is PV to the 1.4. So we're gonna say current pressure. So let's just say I have another one starting. Let's put that up here. So volume. Okay, so let's give 2 spaces. So here I'm going to say put another slider. And this is going to be starting pressure. And then this is going to be in PSI, pounds per square inch. So let's say that this is up to like 1,000 or whatever. Step size 1, minimum value is obviously 1 PSI. So starting, let's say, oops, god dang it, now it's going to have problems. So let's say, 4,500 psi. So obviously that's not going to work. Let's say this at least starts at 100. So 4,500 psi, starting pressure. And so basically the expansion chamber is the starting, and then let's say this one is, next one is tank volume. So tank volume. Let's just find a pinball tank. Let's see. So this is standard. So this is like the size I'm talking about. 48 cubic I'm gonna guess 9 cubic feet, cubic inches. Okay, so 48 inches, cubic inches, let's say, yeah, that's 100 or whatever. And so this is 48. So we have current volume, starting volume, starting pressure. So those are the two things that we need. So let's go ahead and indent this. Now we have, so another thing that you can do if you want to space things out is you could hit space twice and you go into text mode. Then this is okay, so now you want, this is math mode, so we're back in math mode. It's current throw, then we want so we got current pressure, and then so pressure at that spot. So we're going to say pressure at throw. Pressure at throw is equal to PV to the 1.4 is equal to PV to the 1.4. So let's say P1 V1. So luckily I can move this cube here. So you have P1 times V1 to the 1.4 is equal to P2 times V2 to the 1.4. So if we want pressure at the current throw, then we want to divide, so P1 times V1 to the 1.4 over V2 to the 1.4. So that's the equation that we want. So I'm going to say, first do a fraction, and so we have starting pressure times tank volume to the 1.4 over the volume at that point. So volume 2 is going to be basically expansion chamber size plus then this is going to be your throw times the diameter. So this is going to be current throw, so it's pi r squared, so 3.14 times current throw times current throw times the one that you see above there. So this diameter of cylinder over 2 squared. Okay. So let's make sure that this is supposed to be PSI. So something's not right here. Okay. So starting pressure. So that's in PSI, and tank volume inches. So 1.4. Oh yeah, I forgot to do this one to the 1.4 overall to the 1.4. There we go. Alright, so starting pressure 4,500 psi, tank volume 48 inches cubed. And then we're going to go to, I'm curious about what that one is. So let's just have a pressure at throw. So let's have another one that's volume at throw. So we already know what the volume is, because the volume is easy calculation. So volume at throw, expansion chamber size, basically this stuff. Let me see if I can just copy. Let's see if this is even right. Volume at throw. Let's change this to inches. Inches cubed. This volume at throw is 14. Pi. Okay. Oh, so this should be equal to this, but you're adding the expansion chamber pretty much. So that's correct. You know, yeah. So that's correct. So let's change this one down here to. Whoa. Okay, so let's change this to volume at throw to the 1.4. So as basically with that equation, so with the pressure, let's say pressure 2, so let's look at that. So as volume 2 increases, then pressure 1, it should decrease. Right? But that's a massive amount of pressure. But you see, something's not right here, because when I change this, it should be, oh, it is going down. Okay, so it's pretty interesting. So we have volume throw, expansion chamber size plus 3.14 current throw times current throw. So pi r squared current times current throw. And that will give you your volume, and then plus the expansion chamber size at the end. And that's the volume at throw. And so the smaller that is, the more pressure. Because that's a tiny volume compared to the size of the tank, and you're going to have a lot of problems. Luckily, you could put a meter on it, right? So you can put a PSI reading meter on it. So what we want it to do is we want it to drain all that pressure onto a, as it goes all the way throughout the throw. So what we need to do here is we need to find out what our regulated pressure is here. So that's our standard pressure, so let's drop this down until we start to see something that we could actually work with. It's 500 psi is the maximum. It's like, you don't even work with power tools 500 psi. because that's a large tank volume going to a very small volume. Okay. Alright, so now that we got that, now we could actually get to the work part, which is force on piston. Right? Okay, it's force on piston. So we have force on piston. Force on piston is equals to, so you have PSI, so that's pounds over square inch. So what you need to do is you need to multiply the area by the PSI to get pounds force. So force on piston is equals to diameter. So basically what we've been doing up there, 3.14 times diameter cylinder divided by 2 squared. Right? So that's force on piston times pressure at throw. Okay, so now it's in newtons, which is another form, is the metric form of force, which is mass times acceleration. So that's pound force. Okay, so we got 156 pounds force. Okay, that's quite a bit of force. We don't need that much force. And so that's the maximum force, and then as this, so this is basically going backwards. So this would be maximum here. So that's way too much. So here's your maximum throw. So as you get to the end, you should see almost no pound force. And then that's when you know you got the right, when it's fully expanded. You should have almost no pound force. You should have a little bit so it will push through and into the chamber. But even that is quite a bit. So if that's the case, maybe we should expand the size a little bit. As you see, because the volume is 1.4, it's not going to affect it as much as this, especially when the throw is quite a bit bigger than the diameter, right? Okay. So that's pretty interesting. So the video is getting pretty long, so I'm going to probably have to stop here. But we see that we're going to put down quite a bit of force, especially at the beginning to get that piston start turning. We're seeing way too much. Well, obviously the smallest that we start out with is, well, this is overall current throw. So say 0.1 inch, massive amounts, and then it starts to drop off. So this looks good. So from there, we're going to have to do some math to figure out the size of the fan and how much work we can put down on the fan. And then we'll keep going on the calculations on this guy. Alright, so this has been Steven from LegitTechTutorials and Green Engineers. I'd like to thank you guys for watching. If you like this video, please subscribe for more videos like it in this series and our series as well. I'll see you guys next video. Thanks for watching. Take it easy. Peace.